This talk is about web application development, which is typically not the favorite thing of a Haskeller, but perhaps it might become some quite nice thing. So what I ask myself is, with this new development of GHCJS, which is capable of compiling almost all Haskell code to JavaScript, whether it would be possible or how one would develop actual rich web applications. And so that meant I had to find a solution to how to actually write the GUI, how to hook up the event loop, and how to manage the GUI state in Haskell. And then I also needed an application that I could test my approach on. So for this application, the ones who are web developers, there's this standard thing, this to-do MVC project, which is sort of a little to-do MVC list, which is implemented in a bunch of UI frameworks. So let's see whether, right, here we have an example. So what this to-do thing can do is, you can enter something, on enter, it gives you an item, more items. You can toggle them individually, you can clear them, it counts how many are left. Oh, this guy even has done some filtering. You can clear, and we have, to demonstrate that, there's sort of multi-toggle functionality. All right. So this actually exercises, it's a simple application, but still it exercises the framework quite well. If you can do that, then sort of it's quite likely that you can use the same framework to also do some larger applications. All right. So technology-wise, I decided to build the rendering based on React.js, which is Facebook's new UI library, whose the most important concept there is that they actually have a virtual DOM, and when you want to update the actual browser DOM, you just create a virtual DOM and tell, okay, do whatever you need to do to the browser DOM to make it correspond to the virtual DOM. And React.js then figures out how to make that in a browser compatible and most efficient way, or reasonably efficient way.
Double buffering.
Yes, essentially double buffering, and it also makes a lot of sense from a data structure perspective. Namely, if you look at the data structure you need to maintain, the browser needs to maintain for the actual DOM, it needs to track a lot of layout information and dirty tracking for all of this. Whereas for you to describe what you want to have, independent of the actual layout algorithms which are applied afterwards when the CSS styles are given, you can actually describe a lot less. And you can help the browser by sort of computing these differentials yourself. This is nice for us because it means we can just render purely and then say, okay, update. It's a standard game graphics solution. All right, so let's do this in this talk in a step-by-step fashion. Let's try to build this to-do application. And yeah, the first thing for such an application is that you need some notion of what's the state of your UI. I mean, if you think you have a pure rendering function, then you need some notion of what you actually want to render. And so the whole project currently goes under this name Blaze React. So it's React.js bindings using a Blaze HTML style API. The key type is what we have here. It's what I call little web app. It's parameterized over some type you need to represent a state, and it's parameterized over some type which you use to represent actions. And it's just a state machine which can render to HTML. So you have some initial state, you have some way to apply an action to give you a new state, all pure and safe, and you have a way to render, which just takes a state and gives an HTML DOM. And this HTML DOM actually is still a pure representation, which we can then execute against React.js to produce an actual virtual DOM in the browser. So if you have this type, then let's look at our demo application. So I'm starting with the first task of we have this input field where you can create new items, and we want to manage that. So the state that we need to have is at least we need to sort of track the description of the new item. So I create this record for the to-do state. I have the prefix here because I want to use make lenses. For later on, I'll have to update this a bit more deeply. But state representation should be obvious, I assume. So if you have any questions, please just shoot on. So we have our state.
So this is the state of the whole application?
That's the whole UI state. Currently, I'm building it step by step. But this, just for an input field, you want to reflect its value, because then you can render it with the proper value. And we can even do fancy stuff like render the reversed string or whatever. All right, state transitions. Well, on a change event on the input element, we want to create an action which updates our UI state such that it reflects new text that was entered by the user. So there's one action currently. Applying this action to the state, well, nothing difficult. I mean, take the new text, use set from the lens library, which overrides whatever is at TS new item desk. So I'll give you here, oops, that was wrong. This way. Let me give you our state. So that's another type. Yeah, just overwrite it with the new text in the current state. And rendering, here I'm cheating a bit in the talk, in the sense of I actually took the complete application where I copied the DOM from the standard example. But we can look at this. I'm just going to add from my scrapbook step by step. But what we see is with Blaze HTML type API, we import Blaze HTML. So the HTML5 combinators, we import them under prefix H, its attributes under A, because some combinators conflict with the attributes. And then we use the do notation to give us vertical composition. So here we create a section, and this h.bang is just apply an attribute. So we apply the ID attribute, which is set to to-do app. Then we nest in there a div. In the div, to-do wouldn't be necessary currently. We nest a header, again with an ID. Then we actually nest two elements in sequence, an h1 element with content to-dos, and an input element which we name ID for later reference in the CSS. Placeholder step argument, we set autofocus to true, which means React.js will try to focus it. We set its value to the value which we have from our state. And we register an event handler. So if the text input changes, we want to have this. So perhaps the event handler on text input change, it has type tText action to HTML action. Sorry, it's an attribute. So that's the type on text input change. And what you see here is this rendering always says like, I'm going to generate markup whose event handlers will create actions of the given type, such that we later can tie the knot and get that feedback. All right. Now we can define the application. I mean, we just fire it up. We choose some initial state, which we currently set to hello world. And we apply, well, apply action is what we expect, rendering is what we expect. Now let's make it a bit more interesting. So let's just add a paragraph, p reversed, your reversed input, h to HTML new item desk. Good. I hope that compiles. Now, the first thing is, this module is completely pure. It has no dependency on GHCJS. So that means it can be run in GHCI on a server, compiled to native code, whatever you want. This is just the specification of the application logic with one rendering to HTML. So that means to type check, we can just do GHCI to MVC demo. And yeah, that loads. We should be able to test the rendering. Yeah, let's try that. So text place has multiple renderers. We have a string renderer, which I usually use to debug, and we write our test. Simple IO function is put string line. Let's move our state to top level function. String render HTML. Enter to state Q0. I think that should be it. Defined but not used, so we can call test, and we see that we forgot. So down here, we see that our reverse input is not yet there where it should. So let's add that call to reverse. All right, that works. And the one thing that is important to see here is if we define our applications such that they have independence of like the concrete way to run them, that means we can actually have, for example, a test environment where we run them in different fashion and just test the application logic. And these tests, they can easily be run interactively from your REPL. They can be run on your build server without any dependency on, oh, I need a JavaScript environment and everything. Good, but I mean, this talk is about how to make that work in JavaScript. So I have here a main function which runs our demo app, which is really nice. You just say, give me from Blaze React one of the runtime environments, namely the one for React.js. This now does have dependencies on GHCJS. And yeah, run the app, run our demo app. All right. So we go out of GHCI. So I must say that installing GHCJS was really simple. It was just follow the installation instructions. So I have a recent GHC 783, and then go step by step. Take some time because it compiles quite a bit. I mean, essentially libraries from base up. Every library that I wanted to compile, it just went through.
Template doesn't need GHC batch anymore.
No, that's now in there, and it also now has proper template Haskell support, which, as you can see, so I think cabal install minus GHCJS, so it needs a custom cabal install executable, but it's also described in this part of the building. So yeah, what it does is it runs template Haskell by running it on Node in parallel. So in template Haskell, you always have a bit of problem that you can inspect your environment, and your environment partially reflects the host operating system running template Haskell. So that's why you want to sort of have really the environment to be JavaScript such that it's the same as the one that the generated code runs in. All right, so this seemed to work. I have an index.html file which just references the build files in this build directory, and it starts the Haskell runtime system by calling this global system $main with the set encoded reference to the main function. Right, and it references the two style sheets which I copied from the standard example. But there's not really more to it. Let's see whether it works before we do anything else. So I think somewhere I have it open. Yeah, so this points to my to-do MVC. That's the problem if you use styling that is prepared, but Yes, that seems to work at least a bit. Oops. Yeah, so that's pretty neat. Now, during the development of these applications, it would be really nice if you could just inspect the state that the application has and debug it this way, sort of look at, oh, I was in this state, I did that, this action is submitted, that does make sense, how does the markdown look, what are rendering box? And actually, Alex here helped me to develop a generic way to do that. So we implemented like an application transformer, which, sorry, let's go to our demo. Oh, let's just use it in main. So we can import the time machine example, and we can just say with time machine demo app, compile it again, and once you've did an install with cabal install --GHCJS, you can actually just call cabal build. But yeah, so the build system support is still a bit shaky, or at least I haven't enough experience to say exactly how to use it. That's how I'm doing it. Cabal install once, and then cabal build will pick up that is GHCJS. Otherwise, it sort of defaults to the standard GHC, and I didn't find the flag to set cabal build to tell cabal build that you should use GHCJS. It compiled. Ah, okay. Let's reload. There's something on the right. So this is our time machine. So if we now delete stuff, we see the actions submitted. We see the corresponding to-do state to the right, like what was here. If you have some things that sort of work automatically, you can pause the app. So now no actions are submitted anymore. But if you unpause, you're exactly in that state, you sort of continue from there. I mean, it's a standard like undo functionality, but the nice thing is that we get it for free for any web application that you write using this framework. Yeah, I was pretty happy about the time machine once I saw that it could work, and Alex implemented it. It's like, I like that. Yeah, we can always go back to the initial state. And you can imagine like having a state and seeing there's a problem, snapshotting it to a server, and then having your debug facility, which lists you the snapshots that were handed in by your testing team, load that with the corresponding code, debug, fix, check the fix with the same state. I mean, this requires some serialization properties for the state, in the sense of if you have an old state that you can always deserialize it as a new state. But that's a problem which you anyway solve in quite a few cases, and it's well solvable. All right, good. So we're not going to look at how the time machine is implemented. It's not super difficult, but I would like to focus step by step on a to-do example. All right, let's see, what's the next thing for to-do? I mean, it's definitely that we want to have items.
To see that I understand correctly, this with time machine, it's also just a simple pure.
Oh yeah, let's look at a type. With time machine has this type. Yeah, you have a state machine, and you see all the actions applied, so you can just grab them, store them. You can wrap a time machine with the time machine and start an inception. Yeah, it's nice. Yeah.
The React.js type, so the binding from Haskell to React.js, is this written by you, or?
Yeah, I wrote that this week.
And it's somewhere out there?
Yes, it's in a GitHub repository, Blaze React. I mean, it's very rough in a sense. For example, for event types, I just added what I needed, so that it's very limited. But it's sort of straightforward that the construction I used, you could use to do the full set. It has currently a space leak in how it registers event handlers because, well, there's some GHCJS internals that one can also fix, but it requires a bit of deeper hook in a bit of a change to React.js. So the React.js JavaScript library. Otherwise, it's not, so it always does a full DOM re-render. React.js has support for doing partial DOM re-renders and really sort of skipping over whole trees. This support as well, I can see how to build it, but it's not built. So it's not meant for production use. But if you want to play around, I mean, it's very easy to add new event types, to build an application and look a bit how it behaves. But I want to, the thing is really that it doesn't perform as good as it could. So don't expect very good performance. But as you see, I mean, it works. You can very well experiment with it. All right, so we had the time machine transformer. Now, essentially what we want to do is think about extending our state and actions such that we can actually create to-do items. So we have our demo here. And let's just think again about, okay, how do to-do item, well, this is a to-do description, which is some text, and it's a to-do done, which is a bool, and we do, pardon? Oh yeah. Good. And probably it's actually nicer to see it this way. Then we can say that to-do items, or actually, well, let's use a list of items. Item. Should we? Should we go for int map? So the proper way is actually to manage identities yourself and not use indices, because some of the differential, some of the patching, some of the diffing relies on IDs being stable. I mean, it's not going to be wrong, it's just going to be slower, because it doesn't see that actually some elements were just moved. So yeah, that's a bit of a disadvantage. On the other hand, I think it's okay with the list. So we have TS items, which is to-do items. So you see, I mean, I'm using strictness annotations everywhere. But it's not perfectly strict. So the motivation for the strictness annotations is, if you have any data that is long-lived, like the state of your application, you want to make sure that it has this property that if you force the set, that is like what I call fully strict. So if you force the state to weak at normal form, then all data in there is going to be forced to weak at normal form. It's not perfectly true because I'm using lazy lists here. Yeah, this is something that should be fixed by using, for example, the list from strict base types, the library. All right, we have items, and probably we want to register an action which says create item. Yeah, we can actually use nicer names now. And create item actually has no argument. It's just if there is a non-empty text in the state, so let's do our to-do state is new item des. No, let's do it this way. So if we view the new item desk description from the state and it's null, we're just gonna return the same state. No worth creating empty items. Otherwise, we map the items and we prepend a new to-do item, which is obviously not done, and it has then, let's do ourselves a favor. Here. Yep. So for the ones, I'll need to import the function. So over comes from lens, and over is essentially has this type about that form. So if you have something that focuses on a substructure, you can apply a function to the substructure, and well, probably this S to T. Does that make sense for the ones that are lensed? Well, actually, I don't want to explain lens types here. I don't. But you can perfectly understand, I say, look, so focus on this subpart of the pure structure, apply this function, and now what is missing is the function. Prepend this to do item, so the items are a list of items, and I can just prepend one item. And I do this operation on the current state. Good, so then from lens, I need over. I'm gonna do myself a favor and check it first in GHCI for the quick turnaround. Yeah, I'm having some problems with the naming. So here I have my A, and I didn't want that. But actually, no, that's fine. Well, my rendering functions will have the A's in there. And I have to fix it here. Another try. We're missing view, which is just view some part of a structure using a lens. To do state should have 2 arguments. Thank you. So in JavaScript, this would always be reload and test, and then it doesn't work. I like this fix feedback, quick feedback. We don't have any items in the beginning. Well, no, let's make an item. It's false, and give place React talk. Okay. And we also have it in the rendering function. We have the items here, and we're first just going to do, I hope piece work out here, number of items. Well, we're just doing items is 2 HTML of show items. So let's just see whether it interacts properly, and afterwards we render it correctly. HP, it's a do missing here. Blah, 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 blah. Okay, what does it say? All right. I think I'm messing up. What am I messing up? Right, I'm messing up here. Here I have items. So this means it's actually a paragraph just around items. And I want to sort of put something else in there. So what I actually wanted to do is that I want to use the monoidal append in there and say, oh, yeah, just concatenate these contents. And I want to make sure that I have a space in there, then it's going to be all right. Okay. And I'll need data monoid for this to work. It's happy. We can even do the test. Yeah. You see some items down here? Or one item. So let me switch. Yeah, build that stuff.
Are you aware that you are recording in VI?
Pardon?
That you are recording, you are typing in VI. Are you aware of that? Macros open in VI. You press Q by accident, I think.
Ah, that's what I mean. I'm also recording my typing in video. Alright, reload. Yeah, I still have some styling issues, so I'll use the proper rendering. But what we see now, once we have oh, we missed installing the event handler. I mean, it still works here, but we have no way of generating this action that creates an item. And it really looks ugly here, so let's fix these 2 issues. Well, the first one. So what we want to do is when our input field loses focus, we just add a new item. So on blur, see we had the input change, and here we want to do a create item, and we want to rebuild. Reload. If it loses focus, it's gonna add us. So it added it down here, and we can add something more. And we see another bug. Have you noticed it? I messed up that on a create item and I'm not resetting the input text. So here I have a create item action, and the resulting state has both the new item for hello W and the input text here. Well, easy to fix. Set ts new item desk empty string state. So just do two state transitions. And I mean, here I'm sort of doing direct state manipulation. It might well be that once your application logic becomes more complex, that you want to build better abstractions for manipulating your state and implementing the actual handles for the actions. You still pretty surely want to have explicit actions as data types, because this gives you a means on one hand to say, okay, these are all actions that can occur in my application. Plus, for each constructor, you can say, this is the action recording this intention. So they're really semantic. This allows you to ask afterwards, like, oh, in this case, so for this user action, is it really right to generate this action, or should it be something different? And what you see is, I mean, the state updates, implementing them, is still difficult. I'm not doing anything about that. You might consider like switching to functional reactive programming, which gives you an abstraction over a stream of actions and a stream of resulting states, and perhaps that might help. I mean, this framework here is not opinionated of how you manage your state. It just says, tell me how you describe your state transitions, and I'm going to apply them for you. So yeah, this should work. Do I have set imported? I do. One last test, because I really don't like the rendering I have. That should be, that looks better. Another item, another one. And yeah, we can look at how that develops and creates an item. That's okay. So let me copy some. So this to-do example application from which I'm copying is also part of the repository. So let's take the whole rendering stuff. I mean, the rendering is really sort of, yeah, let's look through it and see whether there's anything new. And I don't think so. I mean, I have one thing that if there are no items, we actually ignore a whole piece of the HTML DOM. Then we name our sections. We have checkbox, which is actually a custom combinator to create an input of type checkbox. That's another thing which I would expect you want to do. I mean, we'll be doing that in our backend for using Blaze HTML to render full HTML pages. What you want to do is create your own vocabulary for creating like little subtrees of DOM, such that you don't always have to write these strings. Ideally, the rendering code you write doesn't have any hard-coded strings. I mean, except for UI messages, but if you internationalize, not even this is going to be hard-coded. And all hard-coded strings are part of sort of a module which gives you your language for expressing your GUI. So yeah, checkbox is, but what you see is because Blaze HTML, a Blaze HTML style API is really just a bunch of Haskell functions. You have all the abstraction capabilities. You didn't lose anything. So this is in contrast to templating language where you sort of get thrown back into a Stone Age language, which can do almost nothing. or it can do a lot but doesn't have very good semantics. Alright, so we have a section, we create a checkbox. The checkbox, actually, that's not a nice thing. So we have a number of to-do items that are left, which is just the sum of, oh, where do we have items? Alright, so here up here's our state. Take it apart, new item desk, the edit focus, sorry. We want to get rid of the edit focus, that's a thing for later. Which means we're gonna get rid of it here. Let me just delete that. That's the whole edit stuff. Alright. And I think I need to replace these A's. Yeah, I can do that while we go through it. Okay, where did we? Here I have a few actions which I renamed in our example. And I'm just going to remove all actions which we don't know yet. Create item update. Alright, so here's another nice example. We have the list of items and we want to render them all. So we want to render them actually keyed with their index. So we zip it with a list that gives us the sequence of numbers starting from 0. And fold map just goes over a list, applies a function, and concatenates all the results using the monoidal append, which is for HTML is exactly what we want, just all the tags below each other. And in each case, we just call render a to-do item. For the footer, there's also nothing special. Some inline decision on the item or items, and some conditional logic, some condition that says whether we should show a button that allows us to clear all completed ones. And then some blah. Alright, again, here's some lens magic. Not sure that's the best expression, but I just had fun writing it that way. So, well, it's not a bad expression, but it's suboptimal with respect to readability. I agree. And for render to-do item, we get an item index and to-do item. We conditionally determine its class. We add a key. This is an instruction to React.js. It uses the keys of DOM elements to merge lists. So if it will assign the same item, it will assign DOM nodes such that the same key is mapped to the same key and diff these DOM nodes. One of the important properties that React.js wants to guarantee in its diffing algorithm is that the diffing is linear in time. And there you can't do a full tree diff, but you can do actually a pretty good thing, such that if you help a bit along, you get efficient and quite precise diffs. Alright, here are more event handlers, we're just going to kill them. And that should be it. So we switch back into this mode of using GHCJS to test. Yeah, so we're missing control monad, we're missing foldable, control monad, and we're missing lenses for the to-do items and monoid. Okay, we can fix that easily. And from foldable we get fold map, lenses for to-do items, yes, template Haskell for the win, item, good. Test still works, so now looks a bit nicer. Let's compile. And let me see how much time we spent. Oh, it's gonna work. Alright, to do up. Much better. So on a focus lost, you get a new item, more new items. No, No, no. This still works. Yeah. That's it. Progresses as we want. Okay. So actually, this is the full development workflow for your web app. Start with a simple piece, and now add step-by-step things that are missing. So let's just add click handlers. So for this guy, for these guys, and for the delete. Yes?
Will you also show us the generated JavaScript and show how to interact with JavaScript?
I think it's. I'll definitely. We can now actually. This is a good question.
I don't
So
want to.
No, that's fine. I mean,
spoil
no, it's totally fine. I'm here to answer questions as good as I can. So that means I've looked at the generated JavaScript. I can sort of understand what's happening there. But it is a whole talk, and actually 3 talks, I'd say, in itself, to explain really what's going on and how it's designed. I mean, it's a lot of engineering work. I'm really amazed by what Leute and Hamish Mackenzie have done with GHCJS. I mean, most of it just works. It's in experimental stage. I wouldn't use it for production, but wow, it's cool. It's very nice.
How big is the generated stuff?
Yes, okay, let's look in it. I mean, definitely.
I didn't want to analyze it, just to get an impression.
Yeah. So the first question was how big it is. So it compiles to this build to MVC, and then it has a JSX format, which is just a folder with a bunch of files. The sizes are not as big as you think. So the 4.5 megabyte is also to a large part due to it being using long identifiers, not doing any name mangling up front, and delegating this actually to Google Closure Compiler. So, all right, let's look through it. All.js, well, actually, we have a much better explanation of this here. So, Leite's weblog. Right. So in principle, there's out.js is your compiled Haskell code. Lib.js, the first lib.js is what has to be loaded beforehand. It's runtime system and libraries linked in. And lib1.js is included actually after out.js, and it's due to some staging restrictions. And all.js is just the concatenation of these. What is nice is that if you look at my index.html file, which is just the standard one adapted to point to the right places, that you actually load these files from as separate JavaScript files, just in the right order. And the only thing that changes when you recompile your app is out.js, which means you get actually proper caching for a large part of the application. And you could even split out into multiple ones. So it's not, there's no assumption that it needs to be able to angle it together. Right, so yeah, lib runtime system, lib1 out. Let's have a look at them in the editor. So let's first have a look at the runtime system. So the runtime system actually declares a whole lot of global variables. It is written such, if I understood Leute correctly, that it could easily be wrapped in a function call all outside to have its isolated namespace. The only thing it needs to expose towards the outside is actually the $main and the first and the corresponding argument. So yeah, everything is prefixed with $. These are the registers from the spineless tagless G machine. It manages its stack by its own, so it has initial stack pointer for the initial stack. It has support for thread forking, and then yeah, there's quite a bit of code. I expect some is auto-generated. Other code, there's actually quite a bit of auto-generated code in here. Yeah. Yeah, for example, this code here. This I know from the GHC runtime system itself. This is just application for a function which takes one pointer, one boxed argument, 2 boxed arguments, 3 boxed arguments, and so on. Yeah, and let's have a look at libjs itself. The other thing you get is this files list, so it says what files are included, and you also get the stats which say how big is what library. So here actually we see this HaskellerZ library, which is sort of included as a site, as a dependency of the show function which we use in the time machine. The pretty show is actually adding quite a bit of size. So if the time machine is gone, then it's already quite a bit smaller, or if you implement the show differently there. Anyways, libjs. So these are all libraries. And yeah, what we see is here, this part is sort of, it's GHCJS, and then this C is the set encoding. This is an encoding they use for names to be, well, to remove dashes and unsafe symbols, to just have alphabetic symbols and remove numbers. So it's from the library GHCJS prim, just jump over the set. And then it is the module GHCJS prim, and it's the constructor JSRef, and it's probably the expression for if you hand this constructor as an argument to a function. Then there seems to be some low-level stuff that was included straight away. Here's the Google, I think it's the Google BigNum stuff. So it uses the Google BigNum support to implement integer. What else?
So it seems that it only includes functions that are actually used, because there are so many comments without functions.
Yeah, that might well be. Although, I mean, this, I'm not sure, these comments are not about functions. Or, oh, it might be that these libraries don't have anything which needs to be preloaded. So that said, I mean, I'm not an expert on the runtime system. This is sort of what I've seen. So that's also why I didn't want to spend too much talking about it, because I can't give really solid answers. But yeah, we definitely want to look at what is generated from our code. And what we see is that, how Haskell code is actually executed when compiled by GHCJS is that every function call is translated to put the call on this internally managed stack, return to a main loop. The main loop picks up the next function to execute, calls it, and this way sort of you get tail call support in a language which doesn't have tail call support. It's very similar to the C backend that GHC used to have, or still has, I think. So you can actually see that in, I think in libjs, runsync. Yeah. Runsync is the function that is used when entering in a callback from JavaScript back into Haskell land. So you give it an expression and how to continue, and then it does some initialization, and then here you just see call 10 times, do 10 steps of Haskell evaluation, and afterwards do some checks whether the thread is done, or whether the thread is blocked, how it is blocked, how to react, and then it returns back to loop and loop and loop and loop. Yeah, and then otherwise, I mean, this is just, there's lots of small snippets doing things. Let's see whether we can find something from our code. I would expect that sort of at the end. At the very end, there's a big list of all CAFs, so all top-level functions, because GHCJS also does have some garbage collection of its own and needs to have all roots. So it traverses the stack, it knows about all its stack and all its heap reachable. And about all CAFs. And why does it need garbage collection? It needs garbage collection to, for example, detect whether a thread is blocked on an mvar, which is not known to any other thread. So this means this thread is actually dead. It needs to use garbage collection to run finalizers on weak references. And there's some other use cases. He documents it in his weblog, so please read up there. Okay, top level functions, you can see they're really long, especially the ones from HaskellerZ. So if you throw it through Google Closure, all of these get reduced to, like, probably in this case, 3 or 2 character strings. Yeah, here we saw some functions from demo. Main demo application 215. Oh, that's actually just the string symbol, which is referenced. Yeah, and there's a ton of these functions which just do a bit of stack manipulation and set it all up, the spaghetti code, to run properly. For debugging, there's 2 things. On one hand, if you develop this app such that you can actually inspect it, it's very easy to build a custom debugger. I mean, it would be easy to have a drop down on your state, select a view, store some things, store snapshots, annotate, all of this. Secondly, Leute has mentored 2 Google Summer of Code projects. One about implementing stack traces and a proper debugger in JavaScript. So a debugger which knows about his setup. I don't know, I mean, this is a big project. I'm not sure how far it is, but overall, that is one option that's coming up. And secondly, he also he mentored a project about doing profiling properly, because as we will see when we profile our app, there's just a bunch of functions being called from this run sync all the time. So profiling with the standard JavaScript tools doesn't really work. Yeah, otherwise there's not a lot of interesting things here.
But it reads like the C++ code.
Yes, it's very similar. I think he took a lot of inspiration also from the code generator there.
Is there any chance of having a source map or something?
Yes. There's no. I don't think there's a fundamental limitation for source map. It will still jump strangely, because just of higher orderness. So I'm not sure how that exactly works, but I would expect you can do something reasonably good. Now, on the other hand, it is such that once I've written the bindings, with the bindings I needed to do JavaScript debugging a few times because I didn't manage the callbacks properly. But once I had written that, I didn't see a need to drop down to that level. Then I rather dropped down to extending my time machine support than stepping through functions where in most cases nothing interesting happens. All right. Yes, that brings us to the other question which would be interesting, namely, this is our app. Have a bit of a look at what happens when we profile that thing. So, yeah, we want the CPU profile, we start, we do one render, we stop it. Let's make this, let's just draw it out here. Okay, here's something happened. Let's see what's happening first in this first slice. How do I focus on this? Can I just... Is it shift? Now I got it. Right. Okay, so there's some event dispatching from React.js seems to be independent of us. It takes some time. So, yeah, here it starts. So we have a dispatch event, which in total takes 14 milliseconds. That's okay. Then there's React.js stuff. We don't want to go through that. And here's execute dispatch, and this C. This is the event callback so in my binding, I call a function to create a synchronous callback back into Haskell land. So that this function gives me a reference to a JavaScript function which can be called from JavaScript to execute the IO action I've given it. And that's what we're seeing here. So it's just for a one argument function, yeah, does a bit of management to enter the GHC runtime system again. Okay, back to our profile. The only thing this C is actually doing, as we can see here, it immediately calls runSync, which we already looked at. And then runSync is just like, okay, use these little snippets. Oh, here's an interesting snippet. It calls back into a JavaScript function to actually write to the console log. Let's see what it has written. Oh, that is this message which I put into the event handler to have a bit of debugging output. Good, you can understand that, that makes sense. And afterwards it's doing some other updates. Then, that's interesting. I wonder why C is called like up here without anybody on top on the call stack. In any case, it is about run sync, sync redraw. Right, so what I do to render is that when I get called back for an event, actually instead of immediately updating the DOM, I register another callback for a JavaScript method which is called request animation frame, which means that the next time the browser is ready to display a new animation frame, it will first call my callback, such I can do my DOM updates. So this is what's happening. I expect actually that we just suffered from granularity of the profiler. If it does sampling, then it might have missed the few functions on top of it because they almost spend no time. Right, so run sync, some Haskell world, immediately call into back into JavaScript land, then some calls in React, React, then React render, which calls back via callback to run sync, and now here is the rendering of the DOM. So this creates the actual virtual DOM for React.js, hands it back, and then this whole thing here is React.js doing the updates, differential updates of the DOM. Yeah, so it's not, I mean, the app almost displays nothing, but it's not terribly bad at times. And you can still sort of see from the profile about what is about going on. Well, you can see how control transfers between Haskell land and JavaScript land. All right. Is there something else that you would like to see?
Your HTML file, did you include React.js?
No, I don't need to. React.js is included here. So I have some JavaScript React.js bindings, which is just a few JavaScript functions wrapping React.js, which I build using. So yeah, we can actually look through what it is. So there's one function to create the DOM node, an actual virtual DOM node in React.js, and it is just easier from Haskell to call out here and then do the check whether it's a valid DOM and stuff. Do some reformatting.
So on the top of the screen there is the require React.
Yeah, here I'm including React. Yes. And similarly, I create one React.js class, which I mount at the root, and afterwards its render function will currently always create like a full just virtual DOM composed of React DOM components. So no custom components for the ones that know React.js. So I create this class, and the class is just parameterized over a property on render, which is the callback that it will call on render to get the actual virtual DOM. And I didn't find a way to return from a Haskell callback a value, so I'm just smuggling it out. I create an empty object, hand it over, and it's going to write the value in under the node property. Yeah. Well, smugglers are good sometimes. And yeah, that's all. Mounting an app is just creating some JavaScript data structure, remembering the render callback and the node, and sync redraw app is really the call out to React.js to tell, okay, now update the DOM. Yeah, now actually, if we look at that, we can also have a look at how the bindings actually look.
Yes.
Sorry, where they're obviously in source. Right, what do we need to see? We first need to understand sort of how DOM is represented. So I have a copy of Blaze HTML, which I modified in this library. The extension is mostly the event handler support. And Blaze HTML, the key type is this markup data type, which just says, okay, I'm a markup which can contain event handlers that return actions of type act. And Blaze HTML uses a dirty trick to get the do syntax. It just pretends to be a monad, but it really doesn't satisfy the monad laws. But for the monad types, we actually have to tell what return value we would give if we were to give one. So yeah, event handling is these two additional constructors. I have one constructor to register an event handler. Let me split that. Yeah, so this is currently the event handlers that are supported. So on a text input change, I'm going to give you a text, and then you can do some arbitrary I/O because we're anyways outside of the app, and then you have to return me an action. On a click, you just have to return me an action. The arbitrary I/O is, for example, nice if you want to tag your action with the current time. Because the state is pure, you don't have access to fetching the current time, but you can tag your actions and you can display when the last action happened. And there's also a clear way of how to extend this facility, this construction that I have for the app with support for asynchronous requests. So just forking an I/O action, which will at some time return you an event, an action. All right, so yeah, I can tag some inner markup with an event handler. And the intention is that all the elements on the all nodes in the Blaze markup occurring at the top level, so just being appended to each other, will get applied this event handler. Typically, you use it immediately on a single node. But yeah, that's because we separated. That's the extension, the generalization we need for applying attributes, which has the same semantics. And the other thing we need is that we might have a widget which has a render function which only returns action relative to the widget, like our to-do item. But now we want to do multiple apps, and we want to reuse the render functions from the inner widgets, which means we need to wrap their actions such that we can later dispatch the actions again to the proper widget. So that's why you have a way to say, okay, all actions in this subtree of the DOM should be mapped in the following way. You could even go as far as saying, okay, I'm going to reduce all these actions to no ops. If you like to do that, you can do that. And the rest is just a copy of Blaze HTML. You have a way to represent parent tags, custom parent tags. I mean, this is performance implementation difference, leaves, custom leaves, content, which is when you just write a string. And then we have monoid support, so we can say, okay, please append these two DOMs. And the reason why we represent that explicitly is that this way we have O1 appends and can then sort of reshuffle on rendering. Adding attributes, adding Boolean attributes is something that I had to extend because React.js sometimes really expects an actual bool and not a string. And then again, custom attributes. So this is subject to change for a full React.js support. All right, now, actually, the string render is not that nice. Yeah, let's look at the render itself. So we have two renderers, one rendering to strings. Well, actually, we can look at it. The render to strings is written such that it performs as best as good as possible, and you can actually perform pretty well for strings, even though they're linked lists, by writing everything in a difference list style. And here it's just written explicitly, so that's why you find these strange dots and stuff. But the render just does a simple thing. It traverses the markup and renders and manages what attributes are applied, how to append. Yeah, I think it's not worth spending time on that too deeply. But we'll spend a bit of time on the React.js render. So render itself is a function that currently requires you. Why do I do that? Oh, yeah. Because I have this debug output in the event handler, I require actions to be showable. It's not necessary. I could easily hide that. Then we require a way to call back with an action and a boolean indicating whether we need a synchronous or an asynchronous redraw. Implementation detail, but we want a callback that once we have the action from the event handler, we want to tell our runner, oh, by the way, there's an action that happened, please apply it. And this has to happen in I/O because in the end, you run an app by having an IORef containing your state and just updating that IORef and calling re-renders whenever necessary. We have markup generating actions, so well, we have type, and we get in I/O some React.js nodes. So that's an array of React.js nodes. And yeah, there's a few tricks on how to make that work. I don't know. Well, most of it is ignore the type. I write this type down for me to help me writing these things, but yeah, it's not an easy thing. But if you look at the translation, it's pretty straightforward. If you have a parent, then just with a tag, just convert that to a V node and embed the inner HTML there. And for leaves, it's very similar. For attributes, we somehow set the property on the inner HTML. And for events, what we actually do, and I can explain it. So we somehow need, while traversing this DOM and rendering it, we need to keep track of what attributes do we need to set whenever we render a DOM node. And how I keep track of this is as a function which takes a reference to an object and populates that object as a side effect. So this is this function with a JS object, JS string, so it's just a string-to-string mapping, and it returns nothing, so its side effect is just fill these properties objects. And what you see here is that if you want to convert a tag to a V node, then you make a properties object, so allocate a new JavaScript object, call this IO function which just sets all the properties on that object, and return the object. So this is what we do here. Then allocate a new array. So I do the same trick for children. I just hand over an array which should be filled with the children that are generated. This way I get O1 append, provided the JavaScript arrays have proper performance behavior, but I think they do for push. And so I create this inner children array, I call myself recursively with an empty property setter, and the inner children, this recursive call will populate that all with children, and then I call out to React.js. So here's a foreign import, make React.js parent is just a call to this make DOM node. And then I push that to the children array that was given to myself. So that's the one thing. So this renders the VDOM with all the event handlers in there. Registering an event handler is a bit nasty. Yeah, please look at it yourself. Running it is this kind. Running it is actually reasonably easy. So we have some imports. We have an import for a synchronous redraw, import for mounting an application, and for requesting an animation frame. And then to run it, we append a root element to the DOM, allocate variables to track our state, to track whether we already scheduled a redraw, such that if you have multiple calls to async redraw, that they all get batched, and a variable which we need to tie the loop between rendering and event callbacks, because they sort of circularly reference themselves. Then we need to create an action handler, which is just given an action and information about whether to redraw. does the log message, modifies does an atomic modify IRF. So this is really nice and simple. Just use the apply from the app, and then call out the sync or async redraw. Then we need to create a render callback, which we can hand to the React.js component. And then we allocate a render component, render callback. We mount the app. We set up rendering the loop, do a first redraw, and we're done. Except for currently, if the main thread dies, the whole Haskell runtime shuts down. So I just let the main thread run with a 10-second interval. Yeah, that's it for the whole structure. Another thing which we perhaps could look at, or which is sort of a bit enlightening, is the elements themselves that are generated. So the one thing you see, is a trick that React.js uses in order actually to know what event handler, what actual JavaScript callback to call on an event on a DOM node. Instead of adding the event handlers to the DOM node directly, it has one root event handler for every event type, and puts a unique ID on every element, and it actually has a hash map, well, just a JavaScript property object, I think, mapping IDs to event handlers. This turned out to be faster, and that's why they use it. Otherwise, there's not a lot of surprising things. I mean, it's just what you expect. It's just all of what we have is rendered. Yeah, so inspecting the markup and seeing what goes wrong is easy. And if we switch here, you see the corresponding changes reflected. All right. So I think actually that would be a good point to ask for some more questions if you have them, and otherwise take a break and talk a bit more about Haskell in general. Well, go somewhere else. Yeah.
That's very cool.
Yeah, I'm super happy about it. Alex and me, when working on this time machine stuff, we're always like, Meier is so cool. Oh! Yeah, smiling all the time. It's really nice. But I mean, yeah, developing this was sort of the small piece. The big piece of engineering is really GHCJS and getting that to work. And the other nice thing is, this construction doesn't have any dependency on that it needs to be run with GHCJS. You could as well just make a run app for, well, yeah, just make conditional compilation such that you can also compile it with haste. I mean, the GHCJS dependent pieces are really few. So that means if you get haste up to par that you can do template Haskell, you don't necessarily need it, and that it can actually, well, that it actually works. Then you can just decide for your application, do you need threading or not? And you choose whatever backend you see fit.
Thank you.
Good, you're welcome.
Did you make an evaluation of different Haskell to JavaScript compilers?
Well, there's, yeah, I can give you my take on the landscape. So, what I know from Haskell to JavaScript is Fay, which is, well, actually from Haskell to JavaScript. Currently, there's only GHCJS, which compiles a great subset. Haste is almost there. So they've just recently managed to get proper tail calls and compatibility with GHC783, which is great. So the haste is gonna work at some point. These are the two compilers to JavaScript. Well, okay, then there's some backends for what is it? The AHC. Yeah. For me, sort of the requirement is, I mean, I'm looking at this as how would I develop practical applications using Haskell, and then actually I don't want just Haskell 98. I want GHC Haskell and its library ecosystem. I personally like Lens. I want to use it. I like template Haskell to take over boilerplate. I want to use it. So that, for me, why it's currently clear that, okay, GHCJS. This is also, for me, the reason why I never believed that Fay would be a good alternative, because it just makes so many trade-offs. And has just some subset of Haskell that you anyways then have to, you can't just switch freely between backend implementation and frontend. And as you see now here, there's actually a large part of your code which you would want to implement in a fashion that is backend and frontend compatible. And I don't see why you want to sort of cripple yourself to implement these UI state transitions, because that actually for a real application is going to be quite a bit of work and requires quite a bit of cleverness to structure well. And there I want to just use full Haskell. Similarly for the other approaches, like, well, there's the untyped approaches. And from my experience, I just don't see how you can do refactoring in untyped languages without a lot of pain. And I now refactor quite a few code in Haskell, and it was really as painless. It was for me, I found it a painless experience. It just got told all the places, and once it compiled again, it just worked again. That's also why I wouldn't use ClojureScript, for example, which is a big thing currently on the JavaScript side. And if you look at the other thing is, why I really want to have a fully functional language is, I want to have my precise types and my easy declaration of algebraic data types, such that I can actually structure my application properly and take everything apart. Yeah, that was a lengthy overview.
So how would you extend this with I/O, doing our asynchronous?
Yeah, so that's a very good question. I think we can just check out your branch and have a look at the code.
You could, if I could have actually pushed, you didn't have me as a coverage.
Oh, crap. But that should be quick enough. I can do that.
It doesn't compile.
It doesn't need to compile. I think we just want to see the types. Yeah, the idea is actually pretty simple. So the key thing is that apply action can not only return the new state, but it can also return a list of IO actions which are intended to be run as concurrent threads by the run app. And once they return an action, this action gets fed back to the application, whatever state is there. So, and what you see is additionally, you want to have, apart from the initial state, which is the first thing you transition into and render, afterwards you also want to have some initial requests, because if your application actually depends on some data fetches, then you want to execute these data fetches, because perhaps they are the only things that give you a straight state transition for the next thing. What you see also is that, I mean, these are just IO actions. It is up to you to wrap them up properly. If you need failure reporting, well, your actions need to be able to describe failure. And you wrap up your IO action with catch-all exceptions, and you give back to your UI state a total failure, which means, rendering total failure? Yeah, that should be big crash window. And then we actually have some fun. We have a clock demo implemented as such an app. Probably it's actually better if you explain it, because I haven't seen the code at all.
Yeah, well, it doesn't compile right now. But yeah, it's
Oh, it doesn't compile. Damn it. I wanted to show
I
it.
used to before you refactored them.
Yeah, the refactoring I did is I had an additional type to identify DOM nodes like React does with its React IDs. And that just gave another indirection which was unnecessary. So now I can register these IO actions, but that took some time. Yeah, but we can actually read through the clock app. I mean, the clock app itself should compile, shouldn't it? Let's see. Do MVC clock. Why can't it use to do app?
Well, it's still trying to put document for one, which doesn't exist.
Okay, then let's skip that. Let's just have a quick look, understand what is going on. So our state is obviously maybe a time, because in the initial state we don't have a time and want to show that. No, I don't know what time it is. Rendering is just, yeah, you can see loading phase and then actually some time. Applying our actions, clock action is here. No, we don't need that. Action is just the UTC time at which the action was raised. Scheduling tick works by schedule 1 second later. Is it 1 second? Yeah, a million microseconds. Schedule some action 1 second later, get the current time there, wrap it up as an action. And the initial state is nothing. Initial request is to schedule a tick, and apply clock action sets the time and schedules another tick. And that's all. Now, if you think about accessing a data store in the backend, or accessing something outside your pure UI app, you just do this by make an IO action. Well, yeah. Make an async request via an IO action, and make sure that you have an actual pure state description of a state transition that can model the response that you got from your data store. So what you also notice is actually your action type, if you have a big application, is going to be nested quite deeply. But that should actually be fine. Yeah?
This might be a silly question, but if you have this clock app, which does what I think it does, and have a time machine, and you go back, like, if the app is still running, which was in some cases, right? Does this sort of app bifurcate in some way, or like, how would it behave? What would I actually see if I play this? When do I get ticks?
So if you pause the app and go back in time,
then I get that. Then sort of the clock just goes back.
Yeah, but what happens is when the next tick comes in, I just buffer it. Any ones which were sort of queued up before you paused it, just get them sort of.
But what if I don't pause it and go back?
Then you immediately kill your undo history. So it's like an undo history.
Unwraps all this stuff. So I go back, and then sort of, okay, now I gotta take everything.
Yes.
So then Qt disappears.
Yes. But this is a matter of how you implement the time machine. I mean,
sure, no, I understand.
Yeah.
This should be a 3.
It should be.
Yeah, it should be a tree, and if you actually have these tick events, it's very strange. I mean, the asynchronous events make the tree bifurcate very quickly if you let the app running. Yeah, I think, I mean...
It would be a tree if I wasn't so lazy.
So in production, you would want to write a time machine, which is a bit more expressive and also knows how to compress actions, which actions to drop, and all of this. But this is open to you. I mean, this is just another app.
And then I'll try to do a clock with CSS animations. You just gave me the idea without any JavaScript.
Ah, okay. Yeah. All right. Then, are there further questions? Ah, yeah.
So I don't know whether I mean, I sort of asked back before, but do you have a feeling for what the proportion, I guess, overhead is for something like GHCJS, and when might it become noticeable in real applications? Like, how big do you have to be? How complex does the logic have to be? Does it matter how many libraries you sort of use from the Haskell library? Like, do you have a rough feeling for how this scales in that sense? Or?
Yeah, I can give you a rough answer. So, okay. So first, having more libraries doesn't have an impact on runtime.
Okay.
It has an impact on loading time because all this JavaScript has to be parsed. But that's it. Now, second, I don't know the precise factor. I would sort of currently say, let's say, an order of magnitude. I think that's realistic. That's what some benchmarks showed. So it's 10 times slower, which means that it's going to be 10 times harder to achieve 60 frames per second. Now, on the other hand, if you look at it from how much effort do you really have to spend to develop a client-side app, there your effort, well, what you first want to make sure of is that your effort is always proportional to the number of DOM elements you actually render. So if you cannot guarantee that, for example, you have some data structure, like a program, and you want to check it for compile errors, and you do this check just as a pure function, you can write that, and you use that check during rendering, you're obviously going to be screwed. But then it's a matter of introducing proper caching in your UI state, such that you actually only update, recompute, when the actual base data changes. So this problem is actually even independent. I mean, this problem you have with any application, that at some point you need to do caching to be quick enough to compute everything on display. Then, on the other hand, if it is 10 times harder to get 60 frames per second, I wouldn't attempt to write a game like this if my money depended on it. I would definitely attempt to write it if I want to see how it works and how it behaves. But I would expect that for a proper business app, where you anyways have to take care that the user doesn't have to scroll all the time for ages, you can work around this problem. And you also, it's probably for this application architecture, it's not going to be 10 times, because quite a bit of time you actually spend in DOM rendering or React.js comparison. So this is time any JavaScript implementation would spend as well. And last but not least, I think it is actually relevant. So if you go to like full difficult applications, performance depends also quite a bit on how complex you can do the caching. And there it's definitely much easier in Haskell. I mean, if I have this problem, for example, in our current application, we cache all requests to certain API endpoints, which are essentially fetches of documents. And we don't have we just naive and have a memory leak about how many we cache at the same time. Whereas in Haskell, I would take the PSQs library, take our LRU caching code, just compile it, and I say, okay, I want to cache at most 100 documents, and it just works, and I didn't have to implement anything. Yeah.
Cool. One more question. So your action type is fixed, right? It's a fixed sum type. How would you modularize it? Like if I want to take a library from Hackage which has its own action type.
Yeah, you can see an example in the time machine. You just take your inner action type as a parameter, or if your app is composed of smaller widgets, which you can also see as apps,
yes.
Then you just say, oh, it's an action from this widget. And what is nice is you get complete control over how these actions reach the widget. If you pause the app, actually what's happening is just, we can look at pause. Internal action, paused, just return the state without any requests. Otherwise, apply the internal action. That's all. I mean, what I would be a bit worried about, but I think it actually doesn't matter in contrast to all the other things. If you look at what you have in memory with these, when you nest it like that, then you're going to do long chains of linked lists, I mean, up to the depth of how deeply you nest these items. I don't know whether that becomes a problem or not. I mean, you're going to do all of them for all event handlers, you're going to allocate them. But now, as you see, this is sort of a limited, isolated problem, and I'm pretty sure you could do some impure tricks to actually manage that.
Yeah, I thought Lars was asking a different question. Like your action is, it's not, like, as you said, you will have a huge list of possible actions for any reasonable application. But most of the actions are impossible most of the time. So actions are context sensitive. When you are in one particular state, only a few actions are possible.
Yeah.
And then your state transition function will become ugly. There's a lot of, it's a very, very partial function.
No, if it says most of them, so yeah, I haven't explored that direction of how it looks in the end.
Yeah, I understand it's not a GHCJS question.
No, it's an application design question. So the one thing to note is that there's no requirement for this application for the actions to be a first order type. They could also just be closures. And so in the end, it's a matter of how do you build these closures. And this is, again, as difficult in a pure fashion as it is in an impure fashion. What I expect that in most cases, so what to say, your application state is like a sum type of what view you have, or actually it's, yeah. In most cases, you map actions to just either to the idempotent case, or you would log like unexpected action. And in the end, it's up to you to using the render functions the right actions. And the other thing I would expect is that in many cases you build your app by widget, and you just nest the widget actions internally and just redirect to them. So the top level state transition would actually wouldn't have that many actions. It would just be dispatch to this guy, to this guy, to this guy.
Yeah, I wonder if you can use something like data types a la carte techniques for handling like the different, because it's kind of a simple problem.
Well, if you look at it here, it is such that your application will have a few top-level actions, so actions to its own, and a few actions which it has to delegate to widgets that it uses. So I'm not so sure, and each of these actions has a clear semantic interpretation. I mean, toggle pause app should mean I want to pause this app. So I don't see anything, I don't see redundancy here. I just see the complexity of your application unfolded. What I could see is that if you drop printability, you could drop the completeness, use an open sum type if that makes it easy to extend. And yeah, and it might also very well be that for some of these cases, you're actually going, as said, you're going to use FRP approaches to write the state transitions and generate the actions in the end. It's up to you, but I don't need FRP from the outside to run your app. And I'm pretty convinced that actually making application logic fully pure is a great thing to do. It just, for example, it factors your application correctness into an independent rendering function, which you can just ask, this state, is it rendered correctly? Independent of any transitions happening. And similarly, you can ask, this state and this action, is the transition happening correctly? That is super nice.
Yeah, so actually for asynchronous data fetching, that's always an issue, error handling and stuff. And here you can do that easily because your state can contain something for error handling and retrying requests.
Yeah.
So, yeah, I think it's a lot simpler than just writing directly.
And it's very easy for you to say, save this state, wrap this application in another layer, and
so yeah,
do something on top of it, like
actually,
a crash page. And
this is the cleanest MVC that I have seen so far, where I see all the free layers of the model view controller approach.
Good. I love to hear that.
Yeah, nice.
Yeah. One must say, I mean, Facebook with React.js have sort of made a first step, and they also have a pattern for designing web applications, which they call Flux, which they use in quite a few applications apparently. And it is very similar to that, except what they're not going full out on is purity. I expect partially because purity is so painful in a language, in imperative language. Yeah?
I know that React is losing a lot of time comparing JavaScript objects. So when they're diffing, they have to decide whether a widget changed or not. They have to compare it completely. And the trick that POM does in PhotoScript, because of persistent data structures, they only do reference comparison, and they save a lot of this diffing and over what React.js does by default. So are you doing, or could you do something like this?
I could do the same, but I think it's important to understand the limitations of this approach. This approach is based on doing what we call in Haskell really unsafe pointer equality. And it says, well, if the pointers to these two objects are equal, so in JavaScript, if the two references are equal, then actually these objects are going to be equal. That holds, that's fine. the problem is really the question on what objects are you going to compare. So let's look at our to-do app function. And here a typical case where you would want to compare is on render to-do item. Now what you have to make sure of to make this result, to make sure that you don't have to call the function and can just reuse its result, means you have to make sure that the arguments are in principle structurally equal. And you do that by comparing the reference, well, on this tuple and the edit focus, might be possible. But actually that wouldn't work because the tuple, as you can see up here, is allocated newly on every rendering. And that means that obviously what you should compare is on the int and the reference to the to-do item. And then we would see the equality and it would work out. What I dislike about this approach of or where I see the limitations is that suddenly innocuous changes to your application structure, like a change like this, and not allocating tuples anymore. So that would work fine with the approach of just compare the arguments. Once you change the tuples, it breaks down and performance is bad. So it would mean that every developer needs to really understand precisely when what allocation is happening. So my take on this, yeah, that's the one thing. I consider this approach to be fragile. It's nice, it should be done, it should be used as an optimization, and we should support it. And I can see how one would support it here. I mean, one has to create the custom class, but only once. One would do this as a top-level function using a bit of unsafe perform IO. And then one would override the should component update callback. That would all be fine. But if you look at a complex application, it's actually going to be such. So imagine an application where your widget displays the user that last edited your entry, like the to-do item. So they're synchronized and you display this user. Now, what you display for this user is dependent on the state of, I mean, you either want to show loading because you only have a user ID, or you want to show the actual username. And that means that in this widget deep down there, you really need to have access to the state to ask like, well, is this guy loading or not? Which means that, there's a big chance that you have large state objects which are going to be changed on every action or on many actions being handed deep down in your rendering functions. And then this weak reference trick doesn't help you at all anyways. It only works if your rendering is just aligned with how your state looks. If the rendering is the same as the state, then you can just exploit that we do path copying to gain purity. What I see as a proper approach, so for large-scale applications, if you need caching, you should implement the caching in your UI state properly, track changes properly, so essentially all the data that is mutable, assign it a revision number, track changes based on comparing the revision number for which you computed the function, and compute on demand. And then you actually get predictable performance, and you even get inspectable caches. But yeah, long story short, one can do the same thing, but I don't think it's a panacea as it is currently announced on the internet, like, oh, pure, everything works.
Right.
Thank you.